Hello again. Today we're discussing particulate diagrams or particle diagrams. They are part of one of the ways to represent solutions in AP chemistry. They are used a lot. They look like this, and this is a pretty favored type of questions by students. They find these types of visual representations easy to read and easy to answer. So again, this is one example of a particle or particular diagram. So what do you need to put in here? First of all, the size of this vessel, size of this box represents the volume, and the number of dots, number of particles inside of that volume represents is somehow connected to the number of moles actually. So you will see you can connect this to concentration, you can connect this to the ratio of moles, uh, but it's most correct to say that the number of particles inside this box is connected to the number of moles. Uh, as you can see here, as they mentioned here, so the water molecules are often omitted. So as you can see here, we got a bunch of pluses and minuses in here. So this is something ionic that has been dissolved, and there should be water molecules around it, surrounding it, right? Because that's how dissolving works. But very often, water molecules are omitted because it would just create a mess here, be very difficult to read. Now, you can see here some examples of non-electrolytes and electrolytes. So basically, electrolytes are those substances that dissolve in water, and when dissolved in water, they create ions. So for our intents and purposes, it's good to say just ionic substances, although an electrolyte or a strong electrolyte is a better and more correct term, because some things are not technically considered ionic, but they will still break into ions when dissolved in water. But non-electrolytes are more easy to define. So non-electrolytes are basically uh, polar and non-polar compounds. That's the best way to say it. But like very obvious polar and non-polar compounds. So glucose obviously doesn't have any ions in there they can break apart. Ethanol also. So those are non-electrolytes, and they are represented in particle diagrams like this with no pluses and minuses, obviously. And NaCl and CaCl2 and all these here, those are obviously electrolytes, ionic compounds. So NaCl is represented like this. You have to make sure that the number of blue and red dots, number of pluses and number of minuses are equal, because NaCl, when dissolved, when dissociated, is 1 to 1 NaCl, right? Mole to mole. This doesn't necessarily mean there are six molecules here. Sorry, four molecules here. This doesn't even necessarily mean that there are four moles in here. You will see later how that works. And but it's important for these dots to be 1 to 1 in number. And for CaCl2, of course, you're going to have double the number of negatives. So it's important for blue to red here to be 2 to 1. Sometimes they will not give you this 2 plus. Sometimes you'll just say blue is Cl and red is Ca. So be aware of that. Uh, Now, concentration connected to the number of particles. So, as we said, the size of this volume, the size of this box represents the volume. So basically, we can say here that this here is double the concentration of this. Why? Because here I've got four of moles of these ionic compounds, I can say, and here I've got eight. So again, that doesn't mean that doesn't necessarily mean there are four moles, but what I can say with certainty that I've got double the number of moles here compared to here, and since the volume is the same, that just means that the concentration here is double. Uh, this is that case when you actually have water molecules, so they will occasionally add water molecules here, and when they do, they'll usually represent them with this shape. As you know, water molecules made of oxygen, which is this blue side. That side is partially negative side of the dipole, and these two little ones are gray blue ones are hydrogen. So the negative side of the water dipole has to be turned towards a positive ion. See, so if you draw this in reverse, don't do it because they won't give you points, and vice versa. So the positive side of the ion will have to be turned to the negative. Sorry, the positive side of the dipole will have to be turned to the negative ion. Works the same if you've got another dipole in here. So if I had another big dipole in here, then on the positive side of the dipole, you have the water turned like this, and on the negative side of the dipole, you have the water turned like this. But that rarely happens. Mostly, they will ask you to orient the water in relation to an ion in there. And this is just a little overview of what you need to be careful about when you're working with particular diagrams. I would say that this covers around 90% of the questions. You can see there's a lot of logic in here. So even the other 10%, you can just kind of derive from this logic and make sure you draw it. And especially there are questions where you're asked to actually draw the diagram, and that's not something we can really practice in here. Let's take a look at some examples. So read and let's try to do it by ourselves first. So calcium chloride. Calcium chloride means that calcium Ca to Cl2 is 1 to 2. So here they're 1 to 1. This is good. Here they are 1 to 2. So number of minuses is double. This is not even dissociated, so this cannot possibly be CaCO2 because CaCO2 is an electrolyte. Now, what is wrong with this? A couple of obvious things. So first of all, you got K2SO4, which means you're supposed to have double the number of pluses compared to minuses, and you don't. You've got just 4 pluses and 3 minuses. You're supposed to have 4 to 2 and not 3. So that's wrong. The ratio is wrong. Also, this thing here bugs me because this is undissociated KSO4. Because if this were K2SO4, it's supposed to be 2 red ones, right? Because you got 2 Ks. And also, K2SO4 cannot be not dissociated in water. So that's also wrong. So glucose, you asked to represent 0.1 moles of glucose and 0.1 moles of NaCl. You don't have to draw 6 particles in here. They just chose 6. You could do 5 or 4. Just don't do 2 and 1, as that can create a bit of a mix-up. So if 0.1 moles of glucose are 6 of these little green balls, then 0.1 moles of NaCl are going to be 6 positives and 6 negatives. Why? Because, again, from 1 mole of this, you get 1 Na and 1 Cl, right? So it's just going to look like this if you want these two to be compared and represented as equal number of moles. I mean, this is concentration, but since the size of the container is the same, so concentration will basically mean just number of moles. Okay, this is an easy one. So you've got 3 positive, 3 negatives here, and you've got 6 positives and 6 negatives here. So the volume is the same. So obviously Q is double the concentration of P. Again, number of dots represents the molar ratio. So this means that you got double the moles of Q compared to P, and therefore double the concentrations, and since the volume is the same. And here's the one with water. So which one is correct? And again, the blue side is negative, so the blue side needs to be turned towards the plus. While this here, you got 2 pluses, which is just going to repel. Now, this is a rare type of question. So they're asking, how do you represent this diluted? So basically, you just need to extend the box, double the size of the box. I would just extend it here. They chose a slightly different path, so they just basically instead of the whole, like just resized it to double volume, which is fine. But it's important to keep the number of moles the same. So if you're diluting something, remember, number of moles stays the same. You will sometimes be asked to do this, so you need to draw a particular diagram representing two formula units. This is another term that they will use. Two formula units basically for us just means this is one formula unit or 1 mole, and then if 1 mole is this, what they want me to draw is double. So I have to draw like 4Ks, right? And two SO4s. Right? It's pretty simple. Yeah, this is kind of the most complex one that you can get. So you got silver nitrate and sodium chloride mixed, and then a precipitate of silver chloride forms. So when they say a precipitate, means that this is something which is not dissolvable. So it will stay, it will go to the bottom. So whatever is marked as S, or they say it's a precipitate, just draw it at the bottom, like so. And how many of AgCls you've got? So you had equal volumes of silver nitrate and sodium chloride. And then AgCl, so in AgCl, so Ag comes from silver nitrate and Cl comes from sodium chloride. So if I got three of those, I also have to have three of each of those. So make sure you hit the ratio. Don't draw six of this or something. Hey, see you soon.